I'm Eric Shidley, and this is Astronomy Fundamentalized, Lecture 9, The Solar System. In this lecture, we'll talk about everything in the solar system that is not a planet: asteroids, meteoroids, comets, and dwarf planets. When ancient astronomers looked up into the sky, they immediately recognized that there were some objects that moved independently of the stars. There were objects that would wander from constellation to constellation. In fact, the word planets comes from the ancient Greek for wanderer. These objects that they recognized were, in many cases, the planets. In fact, just looking up at the sky, even today, without a telescope or even binoculars, we're able to see Mercury, Venus, Mars, Jupiter, and Saturn very clearly. Also, from time to time, ancient astronomers would see comets in the sky, and on a regular basis see meteors streaking across the sky, very mysterious objects they seek to explain. Since then, the advent of telescopes, we discovered that there's a lot more going on in our solar system than just those planets. In fact, we now know that our solar system contains 135 moons, one star, 8 planets after we added Uranus and Neptune by the use of telescopes, asteroids, and meteoroids. And so the solar system, it turns out, is quite a complicated and crowded place. Since we were all very young, we learned about the major planets of the solar system, and in the following lecture, we'll talk about those planets in more detail. But for now, I'd like to discuss everything in our solar system, that the extra bits that we've discovered only since the advent of the telescope. Nevertheless, the planets exist, and it's important to mention that we have the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. And then we have the gaseous planets, the Jovian planets: Jupiter, Saturn, Uranus, and Neptune. And then there's Pluto. Well, we all, I think, are aware that in recent years it was determined that Pluto is in fact not classified as a planet. And so instead of having 9 planets, we only have 8. And I suppose all of the textbooks that are printed from now on will be clear of that fact. I've often joked that the reason why Pluto is no longer a planet was perpetrated by publishers to publish more books. But the fact of the matter is there's a good scientific reason why Pluto should not be a planet, and we'll come to that at the end of the lecture. Besides the planets in our solar system, there's a very dense population of asteroids. The asteroid shown here is the asteroid known as Matilda, or asteroid 253. I want to give it its astronomical name. But Matilda was photographed here in an unmanned spacecraft flyby around 1997. And it is considered typical of large rocky objects that orbit the sun in the same way that the Earth does. Most of the asteroids that exist in the solar system are very small, with diameters less than 1 kilometer. But there are 4 that are very large, in fact, and their diameters are 300 kilometers and larger. Their names are Ceres, Pallas, Juno, and Vesta. And here Ceres is shown in comparison to the Earth and the Moon. We remember our scale factor, that if the Earth is the size of your fist, then the Moon is the size of your thumb. And you see here that that's well represented. You can actually hold your fist and thumb up to the screen and notice that they're to scale. And Ceres is shown in scale with that. And so it's quite large indeed, with a size comparable at least to the Moon. And so its presence in our solar system is significant, not to be ignored. Here's our solar system with some of the major planets shown. We see the orbit of Earth and Mars around the Sun, and also in blue, furthest out, the orbit of Jupiter. The important thing to recognize here is that between Mars and Jupiter, at a range of about 2 to 3.5 astronomical units, is a belt in which we find most of the asteroids that are to be found within our solar system. This is known as the asteroid belt, and this is a very densely populated region in space. It was originally thought that maybe the asteroid belt was due to the destruction of a planet due to some tidal forces or some cataclysmic event in our solar system. The modern and most well accepted view of this at this point is that the asteroid belt actually represents a failed planet, a distribution of mass in our solar system that failed to coalesce into a single object. If we were to take all of this asteroid belt and form it together into one enormous snowball of rock, it would turn out to be smaller than the moon. And this is also where we see in green and sort of pink and gray there the orbits of Juno, Pallas, and Ceres, the largest asteroids in the asteroid belt that orbit the sun in the same way that the Earth and Mars and Jupiter do. This is not the only region in the solar system where we find asteroids. In fact, outside of the orbit of Pluto is a region called the Kuiper Belt. The Kuiper Belt is very similar to the asteroid belt in that it contains a very large number of very, very small chunks of metal and rock as sort of our second population of asteroids well outside the I guess you could say the solar system proper. We know that all these asteroids are here because we're able to make direct observation of them with our modern technology. Finding asteroids is as easy as taking a picture of the sky with a relatively long exposure. Here we have a picture where we see a bunch of stars distributed throughout, but there are two that catch our eye in particular, denoted by the blue arrows here. Notice that instead of appearing as dots on the diagram, they appear as small streaks. This is because while the photograph was being exposed, the object traveled a certain angular distance across the sky in that period, and it gives it this distinctive stretched out shape. These objects are asteroids. So we identify asteroids in this way, and it turns out that by now, like over 10,000 asteroids have been cataloged by an organization that dedicates itself to studying these things, known as the Minor Planet Center. But beyond those 10,000 that have already been cataloged, 90,000 or more are awaiting to be confirmed. And in the asteroid belt itself, there may be 1 billion or more asteroids floating out there. Naturally, we haven't spotted them all yet because in order to catalog all of them would be a labor of astronomical observation that just we wouldn't have had time to do by now. Too many asteroids to look at to catalog them all by now. So you might think that with all those billions of asteroids out there, they're one right on top of each other, colliding and banging into each other. In fact, that's not the case. Most of the asteroids are separated by millions of kilometers. So we remember back to our childhood in that video game Asteroids, where you commanded a little spaceship and shooting at asteroids that were all around. That's not a very realistic picture of the way the asteroid belt actually is. It's a very large number of asteroids, but also an extraordinarily large volume of space to contain them in, leaving them millions of kilometers in separation. So here we have another view of the asteroid belt between the orbit of Mars and Jupiter. What I'm particularly interested in this slide is these two regions of asteroids that exist in the orbit of Jupiter. They actually move along with Jupiter as Jupiter makes its orbit around the sun. There is a group of asteroids that lag behind Jupiter and a group of asteroids that travel ahead of Jupiter, and they're called the Trojan asteroids. The ones that trail are called the Western, the ones that precede are called the Eastern. But it's a very, very curious thing that there should be these small clumps of asteroids before and after the orbit of Jupiter. The reason for them is a gravitational resonance, a region in space where gravity, the total gravitational effect of the sun and Jupiter and all the planets and all the whole thing combined, directs these asteroids to accumulate in these places. Very much in the same way as if I took a drum head and sprinkled some iron filings on it and hit it with a mallet. The iron filings would vibrate around the drum head and find locations where the drum head was vibrating the least, and they would accumulate there in a sort of pattern. The same thing is true with the sort of gravitational resonance which suggested for the reason for the existence of these groupings of Trojan asteroids. One concern that we have, and there have been several very, very exciting action film interpretations of, is the potential for asteroids in our solar system that cross with the Earth's orbit. That is, asteroids that have the potential to collide with the Earth at some point. Here we have an example of just one such asteroid. It's called Apollo, and it's not very well behaved in the sense that it is not constrained to move in the asteroid belt, but in fact has an elliptical orbit that brings it closer to the Sun than the Earth's orbit. Therefore, we see there are two locations where the orbit of the Apollo asteroid crosses the Earth's orbit, and so there's a danger of collision. There are two things to appreciate here. One is rather obvious, that in order for the collision to take place, the Earth and Apollo have to be at the same place in space at the same time, and this is a very, very difficult coincidence to arrange. Secondly, there's an awful lot of space involved, and though in this diagram it looks like they would very commonly come across and might hit each other, if I imagine the Earth going around and wiggle, 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 and Apollo going around at a high frequency, they must collide within the next 10 minutes. But the reality is the Apollo and Earth are creeping around in their orbits, and so the collision is very far off indeed. You might imagine that we want to calculate when that collision will take place, and unfortunately it's impossible with any kind of precision to measure the exact position of the Earth or Apollo in the future, such that we could determine whether or not there be a collision. In fact, in recent history, there have been some near misses where asteroids have passed by the Earth very, very closely. I recall one that took place when I was a very young man. I was 19 or 20 years old or so, and I read about how an asteroid passed a distance to the Earth that's equal to twice the distance to the Moon. In a cosmological sense, this is like a bullet whizzing by your ear. It was a very minor story on that particular news day. Nobody seemed to mind. I suppose that's because it did not, in fact, actually crash into the Earth. Had it done so, it would have been a cataclysmic event. Like the one depicted here. This is obviously not a photograph, or you would have heard about it. This is an artist's rendering of an asteroid at least over 100 kilometers in diameter, colliding with the Earth. And certainly we've heard about the speculation that it was an asteroid collision such as this one that resulted in the extinction of the dinosaurs. The idea is that the asteroid collides with the Earth and throws up so much material into the atmosphere that it blocks out the sun. Not only that, it would cause a shower of flaming meteorites all over the surface of the Earth that would produce fires, that would then produce smoke, choking off the planet and resulting in the death of all life not hardy enough to withstand the very low temperatures and the scarcity of food under those conditions. There are several instances or evidence left behind on the surface of the Earth of large meteor strikes. When viewed from space, the area in the vicinity of the Yucatan Peninsula shows a very, very large asteroid crater that is mostly submerged underwater in the Atlantic Ocean and the Gulf of Mexico. And there is a record of a large impact that took place in Siberia in the 1800s, or actually not the 1800s, 1908, I think, was that, which is known as the Tunguska event, when an asteroid struck Siberia and an entire forest was leveled. That was a particularly small asteroid, but there are a large number of significantly large asteroids in our asteroid belt that we might think to be concerned about. The asteroids shown here are certainly much, much larger than typical asteroids. The asteroid shown on the left is Ida, and you can see there, Ida is about 30 kilometers in diameter. You can see off to its right a very, very small object. It turns out that Ida has its very own moon called Dactyl. The asteroid shown at the bottom is asteroid known as Gaspara. And of course, we see again on the right the asteroid Matilda. All of these significantly larger than the typical asteroids. Typical asteroids are less than 1 kilometer in diameter. There are a lot of terms that get out and about we have asteroids, meteoroids, meteorites, meteors, and they're just sort of bandied about rather carelessly. We want to make sure that we get them clear so that we can speak intelligently about these issues. So by definition, an asteroid is one of the thousands of small objects found in the asteroid belt. And a meteoroid is a small rocky object that orbits the sun. It turns out there's no like official distinction between asteroids and meteoroids. Although it's typically accepted that meteoroids are small asteroids. A meteor is the streak that's seen in the sky when a meteoroid is burning up in the Earth's atmosphere. And so the term meteor only applies in the atmosphere of the Earth. When that object reaches the surface of the Earth, if it does not burn up already, and impacts the Earth where it could be retrieved and examined, it's termed a meteorite. Any piece of a meteoroid or asteroid that makes it through the Earth's atmosphere and hits the Earth. It turns out that this has happened quite a few times, and there's a science of investigating meteorites. Here's a picture of a meteor streaking across the Earth's atmosphere, and most of these meteor events that we see are not objects that will arrive at the surface of the Earth. In fact, many of them are as small as a grain of sand. Friction with the Earth's atmosphere heats them up to the point where they produce light, but typically the encounter with the Earth's atmosphere completely atomizes the meteor, and so we don't get a meteorite event. Here's an example of a meteorite, and it's essential that these things be discovered because the only way that we understand the chemical composition of meteorites of asteroids is to investigate the chemical composition of meteors. The reason for this is very difficult to do spectroscopy on asteroids because they don't emit light. There's no emission spectra for asteroids. They reflect light, certainly. The light that is emitted from the sun reflects from the asteroid, which is what makes it possible for us to see it, but they don't emit light of their own, except for their thermal blackbody radiation. And so the chemical composition, being rocky and metallic, is determined by investigating these meteorites that fall to Earth and then are dug up and investigated. Here's an example of a very large crater that is left over from a fantastic impact. This is the Barringer meteor crater. It's located in Arizona, and you can go and visit the thing. It's a colossally large impact, but when you look at it here, you see some buildings down in the middle of the crater. This is only a couple of kilometers wide in impact, meaning the meteorite that struck here was certainly less than a kilometer in diameter, but the impact would have been extraordinarily violent. There are large craters still in existence in various places of the surface of the Earth, as I've mentioned, but there was a time in Earth's history, when there were a large number of meteorite impacts because the solar system was still populated by very small objects distributed everywhere with many Earth-crossing orbits. And so the Earth would have been subject to many meteorite strikes and would have been significantly cratered in its far geologic past. But of course, our Earth has an atmosphere and weather, and erosion takes place, and so the evidence of all of those past meteor strikes, except for the very largest, have all been swept away by time. We can see how that works in comparison just by looking at our own moon. The moon has no atmosphere and therefore has no erosion effects, and so it is pocked with craters. Every crater that ever happened to the moon has left some residual effect on its surface, and so the moon appears to be very cratered, as do almost all dwarf planet and planet-like objects that have no atmosphere, to cause this erosive effect. Periodically, the Earth may be struck by asteroids. It's very hard for us to tell when a large strike would be coming. Remember that there are 10,000 identified asteroids, 90,000 still yet to be verified, and potentially billions in the asteroid belt. This means that we have not identified all the Earth-crossing asteroids, and it could be tomorrow that the big one hits, and astronomers would be taken by surprise. But there is some understanding about the frequency of asteroid strikes, and it turns out that the likelihood of an asteroid strike is associated with its size. Small asteroids strike the Earth very frequently. Many of them burn up in the Earth's atmosphere in the form of meteors. Mid-size asteroids strike more infrequently. Large asteroids, the type of asteroid that could possibly have caused the extinction of the dinosaurs, are far more infrequent, happening only about every 10 million years or so. Aside from asteroids, our solar system is also populated by a very large number of comets. Comets are distinguished first by the fact that they have a different composition. Whereas asteroids are rocky and metallic, comets are composed of mostly ice and rock in combination. A comet has some distinguishing features when we observe them very closely with telescopes. First of all, the comet is preceded by an envelope of hydrogen gas. This is what creates the bright head of the comet that we observe, particularly when comets make close passes by of the Earth. I remember myself seeing a comet, and it was Halley's Comet, which passed close to the Sun, was visible from the surface of the Earth in 1988, going on 1989. I remember because I was a high school student at the time and interested in science and physics and so forth. And the next time that Halley's Comet will return and be visible will be in 2061. But we could see that comet from the surface of the Earth, and it appears as a bright star with a tail streaking off behind it. That tail, it turns out, has two separate parts. There's the ion tail and the dust tail. The ion tail is created by individual atoms which are dissociated from the asteroid and are pushed off from the comet by the effect of the solar wind. Notice that there's an arrow in this diagram that points toward the Sun, and that the ion tail of the comet points directly away from the Sun. This is because the direction of the ion tail is determined by the ionic solar wind, the particles that are ejected from the Sun out into space. The dust tail is actually not atomic, but fine particles of the comet, which have been worn away by a sort of erosive effect. And that dust tail curves away from the comet due to the rotational motion. Inside the comet is the coma, which is the cloud of dust that surrounds the comet, associated with both the dust and the ion tail. And inside is the nucleus, a solid body of rock and ice, which is about 10 kilometers in diameter. If we define the size of the comet according to the hydrogen envelope, it's about 10 to the 7 kilometers. So there's a tremendous difference in size between the hydrogen envelope that envelops the head of the comet and the nucleus itself, which is actually quite small. Here's a diagram of a comet in orbit around the Sun. Notice that unlike a planet, which goes around the Sun in nearly a circular orbit, the orbits of comets are highly elliptical. As the comet approaches the Sun, it picks up a significant amount of speed, and as it recedes away, slows down again. Comets travel great distances through our solar system, and most travel out beyond Pluto before making their return trip. Notice in the diagram that, as described, the ion tail of the comet always points directly away from the Sun, even when the comet is receding from the Sun. So that sort of shows us not to develop the erroneous impression that the tail of the comet is opposite the direction of the comet's motion. In fact, the ion tail is caused by the influence of the sun's solar wind. Comets come from two regions. Previously, I mentioned the Kuiper Belt, and some comets come from that close. The vast majority of comets, however, come from what is known as the Oort cloud, even further out. Notice that the Kuiper Belt is about 50 AUs from the Sun. The Oort cloud is some 50,000 AUs. If we define the solar system by how far out the Oort cloud extends, and the solar system is far larger than I think most of us would have imagined. The Oort cloud is home to potentially two, maybe as many as 200, say 200,000 comets. But not all of them come very close to the sun. There are only a few, like Halley's Comet, for example, that travel out to the Oort cloud and then return to the sun very, very long time periods. Towards the center of the diagram, you can see an example of some comets, and there is one shown that comes very, very close, that lives out in the Oort cloud, but then comes very, very close and actually makes it into our solar system to make a close pass to the sun. This is actually rather rare for comets, but it's what made them first identifiable by mankind, because we saw them in the night sky as they made their trip around the sun. So here's our solar system again, with all of the planets shown, including Uranus and Neptune. The asteroid belt is shown in the region between Mars and the orbit of Jupiter. We see the relative spacing of the orbits and find out that the planets are spaced very close together. The terrestrial planets are very close to the sun, and the Jovian planets get further and further away. And there's Pluto, in an orbit that is inclined at a very steep angle relative to the rest of the solar system. And we, as I mentioned previously, we now know that the classification of Pluto as a planet has been changed, and now Pluto is classified as a dwarf planet. Pluto orbits the sun at the furthest extent of any planet, with the exception of a time period between 1979 and 1999 when Pluto was actually closer to the sun than Neptune. This is another way in which the orbit of Pluto is odd. Not only is it inclined at a steep angle relative to the plane of the orbits of the rest of the planets, but also its orbit is sort of off-center in this way, that it had this exchange with Neptune. Since then, Pluto has receded away from the sun. It's further now than Neptune. But this really isn't the issue about why Pluto is not a planet. The reason is observational astronomy. We've been looking at the asteroid belt and have recognized in that asteroid belt many objects of significant size. For example, 2003 UB313, which I believe is known as Eris. Eris is technically an asteroid, but it's spherical in shape because it resides in the asteroid belt. It's spherical in shape and is larger than Pluto. In fact, is larger than our own moon. So the question immediately arises, if UB313 is not a planet, then why is Pluto a planet? Because of this discrepancy in the description of objects in our solar system, Pluto was demoted to dwarf planet status, as were the many of the other small objects in the asteroid belt. I say small in the sense that they're smaller than the other planets in the solar system, but they're large for asteroids. The large objects in the Kuiper belt include objects such as Xena and 2005 FY9, and Quasar, and EL61. Notice that Xena in particular has its own moon, Gabrielle, whereas Pluto has its moon, Charon. But notice the comparison. If Pluto is a planet, then Xena is a planet. If Xena is not a planet, then Pluto cannot be a planet. And so it's simply been decided that the classification of Pluto should change. So here is a listing of the planets: Mercury, Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. These are the planets. And there are dwarf planets. There's the asteroid Ceres, which counts as a dwarf planet, and Pluto now, and UB313, all classified as dwarf planets in the solar system. In fact, there are a very large number of dwarf planets identified, far too many for me to make a list of, because there are about 50 dwarf planets in the Kuiper belt outside of our solar system proper, and we have the one dwarf planet, 313, which is inside the asteroid belt itself. And then we have the 8 planets, the 4 terrestrial planets and the 4 Jovian planets. And so our solar system is a much more complicated place than it was in the old solar system model. Mercury, Venus, Earth, and Mars, and Pluto with its funny little orbit. That is the simplistic old version of the solar system. But this is the way that it is for astronomy. We look up into the sky and we make observations with more powerful telescopes and we discover more things. We find out that our universe is much more sophisticated than ancient astronomers could possibly have imagined.